Right, so in this video, I'm gonna be explaining another important article about domain adaptation. The title is Learning to Cluster Under Domain Shift. And we have three different types of domain shift: concept shift, label shift, covariate shift, and it is hard to decouple them. Of course, some people talk about conditional shift as well. So this paper in 2020, while unsupervised domain adaptation methods based on deep architectures have achieved remarkable success in many computer vision tasks, they rely on a strong assumption: label source data must be available. Because in privacy concern, for privacy protection, they have these. There are some approaches that we use. We get the data. We don't have access to this black box, but we know the input-output, and that's why different companies, different enterprises share their data. They're sharing their models, not the samples of the data itself. So that's a good way to keep the privacy. So in this work, we overcome this assumption and we address this problem of transferring knowledge from a source to a target domain. When both source and target data have no annotations. Inspired by recent works, of course, this could or could not be used for privacy protection and those issues, information privacy and those things. But so they keep it very open. They say that when both source and target have no annotations. Inspired by recent works on deep clustering, when you don't have any annotation, the first things comes about that it's a clustering. And yes, so inspired by works on deep clustering, our approach leverages information from data gathered from multiple source domains to build a domain-agnostic clustering, which is then refined at inference time when target data become available. Specifically, at training time, we propose to optimize a novel information theoretic laws, which coupled with domain alignment layers ensures that our model learns to correctly discover semantic labels while discarding domain-specific features. Importantly, our architecture design ensures that at inference time, the resulting source model can be effectively adapted to the target domain without having access to source data, thanks to feature alignment and self-supervision. We evaluate the proposed approach in a variety of settings, considering several domain adaptation benchmarks. So you see that in the unsupervised domain adaptation, a model is trained combining labeled images from one or several source domains and unlabeled images from the target domain. In the unsupervised clustering setting, unlabeled images from the same domain are grouped into visually similar images. We introduce the unsupervised clustering under domain shift setting, where we leverage unlabeled source domain data to improve target domain clustering. By the way, I have a playlist about contrastive learning, both in unsupervised and supervised and semi-supervised setting. It is related to these ideas. Deep clustering. Over the last few years, unsupervised representation learning has attracted considerable attention in computer vision. So This reference makes use of an autoencoder to produce a latent space where cluster centroids are learned. So we assume that to observe S source domains, I sub S composed of images. I stands for images of source, each depicting an object from C different object categories. So we assume that C is known a priori, but we do not dispose of image labels. We propose to learn image representations, allowing to cluster source image according to the unknown category labels. Our goal is to adapt a representation learned on the source domains in order to predict labels on the target domain. So these are the images of the target domain. In this adaptation stage, we consider that we do not dispose of the images from I1 to I sub S. So we employ deep neural networks from images to that latent space, to the network output Z, that can be interpreted as probability vectors. So first we do training on sources. Different domain 1, 2, 3. And then so in the training stage, images are clustered by maximizing this mutual information. So clustering is based on mutual information. Domain alignment is addressed combining a batch normalization alignment technique with a novel mutual information minimization formulation. In the adaptation phase, which is this one, in the adaptation, still we're using this mutual information. Domain shift is handled by combining this batch normalization alignment with a specific mutual information maximization procedure. So we are in the multi-domain clustering with mutual information. So this all images of the source, both I and D are treated as a random variable. We consider that we dispose of a set of image transformations. So this double objective can be achieved by maximizing the mutual information between the predictions from I and I prime with respect to network parameters. And the Z and Z prime are the network cluster assignment predictions. These two, network cluster assignment predictions. To estimate the mutual information, we need to compute the joint probability of cluster assignment. Probability that Z is C or Z prime is C prime, because we have different domains. We have C domains, so this could be any of them. So this probability is estimated by marginalizing over the current batch. Let us assume to observe a batch composed of n unlabeled images. So we can estimate the marginal distribution. So it's just a summation over S and N. And the mutual information is then very simple to calculate. Because we have this P sub C. And now we are talking about domain alignment. Training the network only via this maximization of this mutual information may lead to solutions where input images are clustered according to domain information that rather their semantics. To tackle this problem, feature distributions from different domains should be aligned in such a way that the classifier cannot cluster images according to the domain. We propose to address this domain alignment problem by the combination of two complementary strategies. First, we have proposed to formulate domain alignment as a mutual information optimization problem. The key idea of assets alignment strategies is that the cluster assignment Z should be independent from the domain D of the input image. Consequently, the mutual information between the predicted label Z and the image domain D must be minimal. So, to this end, we estimate the joint probability distribution by just marginalization. So we consider that we observe S batches of images, one from each of the source domains. So we can compute the batch statistics for each domain separately. What are them? There are mean and variance. But for a given input X computed from an image of domain S, the output of the normalization, you're just normalizing it. So simple. And this gamma and this beta are the usual affine transformation of this batch normalization layer. When we combine them, this is the total minimization. Mutual information between Z and Z prime, between Z and D, and finally Z prime and D. But for improving the stability, the computation of mutual information is based on the estimation of marginal probability matrix. And following a standard stochastic gradient descent approach, this matrix is computed for every batch. However, estimating the full probability matrix from small batch can be inaccurate. So, considering that P sub CC prime is the matrix associated to current batch. So this one is the current batch. The mutual information can be, because this one is the probability estimated on the, we have the previous, this is the previous batch, and alpha is just a dynamic parameter. It could be anything between these two extreme cases. Then we have adaptation to the target domain. We propose to treat images with a prediction confidence larger than a threshold epsilon.